Attention for final countdown. 3, 2, 1, Vulcan ignition.
Allumage DAB.
This is the Ariane 5, a rocket 52 meters tall, 5.4 meters wide, and weighing 777 tons when fully fueled with 170 tons of liquid fuel and 300 tons of solid fuel. This entire machine produces 13,300 kN of thrust, equivalent to the force generated by 45 Boeing 747-8E engines, combined the current fastest commercial aircraft in the world. The cost of this entire machine is $130 million. This is the most successful rocket of the European Space Agency, with more than 82 successful missions launched into space since it became operational. But on a morning in 1996, during what was supposed to be its maiden flight, less than a minute after launch, the rocket abruptly veered off its flight path, generating a gigantic aerodynamic force that led to its explosion in front of thousands of people watching the launch. The cost of that explosion was about $500 million, including the payload on board and the rocket itself. But what went wrong? In 1973, 11 countries collectively called by the European Space Agency decided to take Europe on its own path in the space field. 6 years later, in 1979, the first rocket, called Ariane 1, was launched from the Kourou Space Center in French Guiana, followed by Ariane 2 and 3. After extensive years of research and development, the European Space Agency had already gained experience with the development of the Ariane 1, 2, and 3 rockets. And with that, the fourth version, Ariane 4, was launched. The rocket reached a record of 113 successful launches and proved to be ideal for launching communication satellites into low Earth orbit. But it was time to develop a new rocket with greater range and higher payload capacity. So, work began on the creation of what would come to be called Ariane 5 with a new design, 6 meters shorter than its predecessor. 4 gigantic fuel tanks, 138 tons of thrust produced by the main engine, called Vulcan, 2 side boosters, each producing 500 tons of thrust. New fairings, 12 sequence stages, new systems and modern computers, as well as a greater payload capacity. After a decade of development and about $7 billion invested, the 5th version of the European rocket family was born, Ariane 5. During its development, some systems from Ariane 4 were used in the new Ariane 5, since Ariane 5 was designed to be an evolution of its predecessor, Ariane 4. Although they don't have the same design, both were built to have a very similar flight profile and dynamics. Some of these systems brought from the old Ariane 4 to the new Ariane 5 included the inertial reference system, which provides the rocket's computers with data about the rocket's orientation. In other words, whether the rocket is pointing up or down, data that indicates if the rocket is turning or not, speed data, acceleration data, as well as data that shows if the rocket is spinning on its own axis, among several other critical parameters for the rocket's flight. This system uses laser gyroscopes and accelerometers mounted on a fixed platform. All this data is processed and sent to another system, which was also borrowed from the old Ariane 4, the flight control computer, or the flight control computer, which ran the same software as the old Ariane 4, the operating system called ADA. During the Ariane 5 certification process, several tests were carried out to verify the integrity and compliance of the various onboard systems. But the technical team, along with some engineers, disregarded the need to carry out tests, as well as the review of the systems responsible for the rocket's flight, including the inertial reference system and the flight computer. Since the Ariane 5 would have a flight profile very similar to that of the Ariane 4. So, in the view of the technical staff, it would not be necessary to make any changes or modifications to the computers, nor to the code. Little did they know that this lack of review of the systems would cost them $500 million. On the morning of June 4, 1996, the Ariane 5 was transported to the launch site for what would be its maiden flight. On board were 4 research satellites that were part of the cluster mission for investigating the Earth's magnetosphere and its interaction with the solar wind. The 4 identical satellites would fly in a tetrahedral arrangement, and each weighed 1,200 kilograms. The weather conditions were favorable and the fueling process began, starting with the liquid helium tank and then the main tanks, which were filled with liquid oxygen and liquid hydrogen, both at cryogenic temperatures. On the launch pad, 2 small rockets assist in the ignition process of the main engine of the rocket's primary stage, called Vulcan. About 6 seconds later, the 2 side boosters are ignited and the rocket lifts off from the launch pad. Babe ignition. Everything goes as planned, and the vehicle follows the expected flight path. But at 37 seconds into the flight, at an altitude of about 3,600 meters, the flight control computer sends a signal to the 2 side boosters, as well as to the main engine, to deflect the nozzles to the maximum position, and this leads to aerodynamic stress that causes the rocket's destruction and explosion at 39 seconds into the flight, at an altitude of 4,000 meters. Meanwhile, everything that was left from this explosion was scattered over an area of about 12 square kilometers. Okay, but what happened with the computers and electronic systems? Computers only understand zeros and ones, which means all the information that goes into a computer, from huge text to numbers, is all turned into zeros and ones. And each letter or number is represented by a well-defined set of zeros and ones, the so-called bits. Let's consider a 4-bit integer. A 4-digit integer bit allows you to store any number ranging from 0 to 15. If we want to store, for example, the number 16, this will cause an error because the maximum limit for a 4-digit integer bit is the number 15. So we need a larger integer bit to store the number 16. So with a 16-digit integer bit, we can store any number ranging from minus 32,768 up to plus 32,767. But any number greater than that, and again, we'll get an error. Going back to the rocket, inside the Ariane 5, there were 2 inertial reference systems with the same hardware and software, providing data on position, speed, rocket tilt angle, among others. There were 2 identical flight control computers that managed the rocket's flight. If one failed, the other would take over. Inside the inertial reference system computer, the rocket's horizontal speed data was stored in a 64-digit bit float variable, which allows storing real numbers, both positive and negative, from billions of possible values. So the computer obtained the data, stored it in a 64-bit variable, converted it to a 16-bit variable, and sent it to the flight control computer. In the first seconds of flight, these conversions were done without any problems because the rocket's speed was still low, similar to its predecessor, Ariane 4. But at 36 seconds into the flight, when the speed was already quite high, higher than that of its predecessor, Ariane 4, the system obtained the speed data and stored it in the 64-bit float variable. And when it tried to convert it to the 16-bit integer variable, an error occurred and the system shut down. The second backup inertial reference system takes over and tries to do the same conversion again, and again an error occurs, and the system sends this error instead of the speed data to the flight computer and shuts down. With both inertial system computers inoperative, the flight computer tries to take some action about it. And since there was no protection, not even lines of code telling the flight computer what to do. In these cases, the flight computer thinks it is completely off the planned flight path and tries to correct it by sending a signal to the two side boosters, as well as to the main engine, to deflect the engine nozzles to the maximum position in an attempt to correct the deviation from the trajectory, which in reality does not exist. And this leads to the destruction and explosion of the rocket at 39 seconds into the flight.